KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with example 11. After completion of this example problem, we will go to discuss exercise problems from the same chapter, alternating current. Okay, see here. First, see this example problem 11. Right. First, see the problem, then we will go for solution. Show that in the free oscillations of an LC circuit, the sum of energies stored in the capacitor and the inductor is constant in time. So, I will repeat once again, you please be concentrate what he is asking. Show that in free oscillations of an LC circuit, the sum of energies stored in the capacitor and the inductor is constant in time. So, what is LC circuit and what is a capacitor and what is inductor? That's what we discussed in our previous problems also we discussed, and in our theory also we discussed, right? Okay, capacitor is a device which stores energy in the form of electric field. Inductor is a device which stores energy. Inductor is a device which stores energy in the form of magnetic field, right? In our problem, in this example problem 11, the main thing is LC circuit, and we have to show that the free oscillations of an LC circuit, the sum of energies stored in the capacitor and the inductor. Generally, the formula to calculate energy stored in the capacitor will be of CV square. The formula to calculate energy stored in the inductor will be 1 by 2 Li square. Okay, right, that is the general thing. And here the sum of energies stored in the capacitor and the inductor means what? 1 by 2 CV square plus 1 by 2 Li square is constant in time. Generally, even from some mathematics point of view also, in one expression, when that expression or equation which is depending upon time, then we cannot say that which is constant in time. When the equation or expression what we are going to get which is independent of time, that only he is asking. See, that is what energy stored in the capacitor and the inductor is constant in time. Okay, right. See this. See the solution. Let Q naught be the initial charge on a capacitor. Let Q naught be the initial charge on a capacitor. Let the charged capacitor be connected to an inductor of inductance L. Let Q naught be the initial charge on a capacitor. Full stop. Let the charged capacitor be connected to an inductor. Of inductance capital L. Please try to understand. He is explaining the scenario. He is explaining the situation, how it is going to give the required answer or required output what he is asking according to the question. So here let Q naught be the initial charge on a capacitor. Let the charged capacitor be connected to an inductor of inductance L, capital L, full stop. As we have studied in section 7.8, right. So in our previous example problem, in the example problem, that is what 7.8, there we studied, right. As we have studied in section 7.8, this LC circuit will sustain, an oscillation with frequency, okay. Right, here as in section 7.8 means not only example 7.8 that is what the theoretical section, he is saying that theoretical section, that is what LC oscillations, in that section we studied. So this LC circuit will sustain on oscillation with a frequency omega is equal to 2 pi nu, that is equal to 1 by square root of LC. So this is also we also derived in that section, right. So omega is equal to 2 pi nu, nu is the frequency of oscillation and that is equal to 1 by square root of LCM. L is the inductance and C is the capacitance. Now at any instant small t, charge Q on the capacitor and the current I are given by. So that is what Q is equal to Q naught cos omega t, Q as a function of time. So here he is saying clearly, at any instant t, charge Q on the capacitor and the current I are given by Q of t is equal to Q naught cos omega t, I of t is equal to minus Q naught omega sin omega t. You know very well I is equal to dq by dt, you know very well I is equal to dq by dt. Okay, here Q is equal to Q naught cos omega t and I is equal to minus Q naught omega sin omega t. So because I is equal to dq by dt and here this Q and this I both are as a function of time. So this Q is a function of time and this I is also function of time. Now energy stored in the capacitor at time t is, energy stored in the capacitor at time t is, small t is UE is equal to half CV square, that is equal to 1 by 2 into Q square by, these two are same. This is the formula for energy stored in the capacitor in terms of capacitance and potential difference, and this is the formula in terms of charge and capacitance, that is the only difference, right. And the same thing, because Q square by 2C, here we are saying UE is equal to Q square by 2C and Q value we know Q naught cos omega t. So if you write Q value here, finally we are getting energy stored in the capacitor at time t as UE is equal to Q naught square by 2C, cos square omega t, right. Now energy stored in the inductor at time t is, so this is what regarding the capacitor and this is the energy. Regarding the inductor, what is the energy stored? Energy stored in the inductor at time t is is equal to 1 by 2 Li square, right, 1 by 2 L, and I value we know minus Q naught omega sin omega t. So here in place of I we are writing Q naught square omega square sin square omega t, Q naught square omega square sin square omega t. This is what the formula for I, that is equal to Q naught square by 2C sin square omega t, Q naught square by 2C sin square omega t. This is what observe carefully, see why he is writing Q naught square by 2C and this is what sin square omega t, because Q is equal to Q naught cos omega t, Q is equal to Q naught cos omega t. So here Q naught square as it is, and after completion of this, you know the formula omega is equal to 1 by square root of LC, right. So they are also given and we are utilizing this here, this here, because in place of omega you can write 1 by square root of LC, 1 by square root of LC, then omega square is equal to 1 by LC, no, 1 by LC. When it is 1 by LC, okay, when it is 1 by LC, here already L is here, L will get cancelled, C is the remaining thing. Finally here Q naught square by 2C into sine square omega t, sine square omega t, okay, right. Now sum of energies stored, that only he is asking, no, he is asking that the sum of energy stored in the capacitor and the inductor is constant in time. So sum of energies, so mathematically UE plus UM is equal to Q naught square by 2C into cos square omega t here, and it is sine square omega t. Q naught square by 2C into cos square omega t plus sine square omega t means it is 1, no? Cos square theta plus sine square theta is equal to 1. So here cos square omega t plus sine square omega t is equal to 1. When this is equal to 1, when this is equal to 1, UE plus UM, sum of energies is equal to Q naught square by 2C. Right, now this sum is constant in time. This sum is constant in time as Q naught and C, because Q naught is the C here. What is the Q naught, no? Is the initial charge. Q naught is the initial charge on a capacitor, right, which doesn't vary with time. Initial charge on a capacitor. And next C is the capacitance, no? Both are time independent. So that's what starting I told you. So to show that, we have to say that the sum of energy stored in the capacitor and inductor are time independent. The sum is constant in time as Q naught and C, both are time independent, full stop. Note that it is equal to the initial energy of the capacitor. It is equal to the initial energy of the capacitor, because what is the initial energy of the capacitor? When Q naught is the initial energy on a capacitor, the initial charge, when Q naught is the, when Q naught is the initial charge on a capacitor, what is the initial energy? Obviously Q naught square by 2C, no? Formula is Q square by 2C, Q is equal to Q naught, then initial energy is Q naught square by 2C. When initial energy is Q naught by square by 2C, and this is what here we also got the same, no? So that only he is saying, it is equal to the initial energy of the capacitor, okay, right. Next, exercise problems. So example problems completed from this chapter, alternating current. Now we are going to discuss, we are going to start exercise problems. See here, see this. First exercise problem, exercise 1. A 100 ohms resistor is connected to a 220 volts 50 hertz AC supply. So it is the resistance of a resistor, and it is the voltage, AC voltage, and it is the frequency. A 100 ohms resistor is connected to a 220 volts 50 hertz AC supply, full stop. There are two things we have to solve and we have to find out. One is, what is the RMS value of current in the circuit? B is, what is the net power consumed over a full cycle? A is, what is the RMS value of current in the circuit? B is, what is the net power consumed over a full cycle? See here, answer. Here R is equal to 100 ohms. R is equal to 100 ohms, that is what they have given. It is RMS is 220 volts, right, given, and F is 50 hertz, right. Now A is, what is the RMS value of current in the circuit? I RMS is equal to epsilon RMS by R, that is equal to 220 divided by 100, that is equal to 2.2 amps, because 0 will get cancelled. Finally write 2.20 or 2.2. 2.20 amps, that is what the RMS value of current, what he is asking. So this is the formula, I RMS is equal to epsilon RMS by R, and these two values they have given, that is 220 volts this one, and this is what 100 ohms. So finally we are getting I RMS as 2.20 amps. Next B. So here, what is the net power? What is the net power consumed over a full cycle. So what is the net power consumed here? You know, P average is equal to, the formula is V into I ma, otherwise epsilon RMS into I RMS. So epsilon RMS already given as 220 volts and I RMS given as, I RMS we calculated. So in A we calculated, and which we got as 2.20 amps. 2.20 amps. So finally here, if you multiply these two according to the formula, if you multiply these two, we are getting, finally we can get, and we are getting 220 into 2.2 means 2.2, you can write 22 by 10 now. So 0 will get cancelled. After 0 will get cancelled. After that 220 into 2.2 means 220 into 22 by 10. Then 0 will get cancelled. Finally 484 watt. That is what P average. So that is net power consumed over a full cycle. Net power consumed over a full cycle. See here ma. So which is what he is asking, that we calculated the net power consumed over a full cycle is 484 watt. 484 watt. Now next problem, that is exercise 2, second exercise problem. See here. Here also we have two things, A and B. First A. So the peak value of an AC supply is, the peak value of an AC supply is 300 volts. 300 volts, full stop. What is the RMS voltage? What is the RMS voltage? Right. Next B. The RMS value of current in an AC circuit. The RMS value of current in an AC circuit is 10 amps. Is 10 amps, full stop. What is the peak current? What is the peak current? Right. So finally, in A we have to calculate RMS voltage. In B we have to calculate peak current. But given epsilon naught as 300 volts. Right. So epsilon naught as 300 volts. That is, here epsilon naught is equal to 300 volts. Then epsilon RMS is equal to, you know, the formula is 0.707 epsilon naught. 0.707 epsilon naught. Here 0.707 into epsilon naught is 300, no? 300. That is equal to 212.1. 212.1 volt. That is what epsilon RMS. That is what RMS voltage. That is what RMS voltage he is asking. So that's we got it as 212.1 volts. Now B. So in B they have given RMS value of current, but he is asking peak current. So what is the RMS value of current? They have given 10 amps. So when RMS value of current has 10 amps, for peak value of current or peak current, I naught is equal to root 2 I RMS. So root 2 means 1.414, no, that's value we are writing, into 10. So finally we are getting 14.14 amps. That is what peak value of current. Right. Next, third exercise problem. Third exercise problem. See here, a 44 millihenry inductor is connected to 220 volts, 50 Hz AC supply. Full stop. Determine the RMS value of current in the circuit. Determine the RMS value of current in the circuit. Right. Here, you know, the inductance they have given as 44 millihenry. That is equal to 44 into 10 to the power of minus 3. 44 into 10 to the power of minus 3 Henry. Because milli means 10 to the power of minus 3, no. Next, epsilon RMS is equal to 220 volts. 220 volts. F is equal to 50 Hz. F is equal to 50 Hz. That is what frequency. Now here reactance XL is equal to 2 pi F into L. So 2 pi into, that is what 50 is the frequency, and L is the 44 into 10 to the power of minus 3. 44 into 10 to the power of minus 3 ohms. That is what reactance. Next, current. That is what he is asking now. Determine the RMS value of the current in the circuit. So this value we need not to calculate because he didn't ask this. He is asking RMS value of current. So RMS value of current is equal to epsilon RMS divided by XL. So which is 220 now, which is 220 and given in the question. XL, this value you can write directly, and now you can get now we have to do mathematical process, mathematical calculation, so that we are getting here 15.9 amps. 15.9 amps, that is what RMS value of current, that's what he is asking. So that's what we got it as 15.9 amps. 15.9 amps. Okay, right. So in this class we discussed 4 problems, 1 example problem, and rest of the 3 exercise problems, right? So regarding these problems, first in example 11 it's very clear and important problem also. In example 11 problem, we calculated sum of the energies stored in the capacitor and an inductor. Sum of the energies stored in the capacitor and an inductor. So that's what we got. That's what we calculated. We need to according to the problem, we need to calculate UE plus UM. Okay, and let if Q naught be the charge, initial energy stored in the capacitor will be Q naught square by 2C. It's okay, but if you continue the problem here, let the charged capacitor be connected to an inductor of inductance L, means, right, what we learned from section 7.8, that is what LC oscillations. We know this, that is omega is equal to 2 pi nu, that is equal to 1 by square root of LC. And as a function of time, this is the Q charge at any instant of time, and it is the current I at any instant of time, small t. So which is Q naught cos omega t, and this is Q naught omega sin omega t. Now energy stored in the capacitor at a time t is, right, this is the formula which is 1 by 2 CV square. 1 by 2 CV square, that is equal to 1 by 2 Q square by C. 1 by 2 Q square by C, that is equal to Q naught square by 2C. Q naught square by 2C cos square omega t. This is what energy stored in the capacitor at time t. Next, we calculated energy stored in an inductor. The inductor at a time t. The formula is 1 by 2 Li square, that is equal to 1 by 2 L Q naught square. Q naught square omega square sin square omega t. Sin square omega t, that is equal to Q naught square by 2C into sin square omega t. So finally sum of energies means if we have to add this one and this one. So finally we are getting, because of this cos square omega t plus sin square omega t is equal to 1. Here we are getting Q naught square by 2C. Right, when it is Q naught square by 2C, we can say the statement, that is what the sum is constant in time as Q naught and C both are time independent. Both are time independent. Note that it is equal to the initial energy of the capacitor. It is equal to the initial energy of the capacitor. Okay, right. Next, exercise problems. So first exercise problem is, here by giving the resistance of a resistor and which is connected to the AC source of 220 volts and 50 Hz, he is asking to find RMS value of current. This is the formula. So ARMS is equal to epsilon RMS by R. These two values they have given. Finally we got RMS value of current as 2.20 amps. Next, he is asking what is the net power consumed over a full cycle. So the formula is epsilon RMS into IRMS. 220 into 2.2 means that is 484 watt. 484 watt. Next, exercise 2, right? In this exercise 2, see here, he is asking what is the peak value of an AC supply. He is 300 volts, right? That is the given value. He is asking what is the RMS voltage. By using this formula, epsilon RMS is equal to 0.707 epsilon naught. We got that value as 212.1 volt. Next, he is asking the RMS value of current, he has given in BM, they have given RMS value of current, but asking what is the peak current. This is the formula. I naught is equal to root 2 into I RMS. I naught is equal to root 2 into I RMS. And by substituting the given values, we got it as 14.14 amps. 14.14 amps. At last, in this class, exercise 3. So here they have given inductance of an inductor connected to the AC source of 220 volts and 50 Hz. He is asking what is the RMS value of current in the circuit. Here L is equal to 44 millihenry, 44 into 10 to the power of minus 3 Henry. Epsilon RMS is equal to 220 volts and F is equal to 50 Hz. Reactance XL is equal to 2 pi F into L. So by substituting the values, this is the product or this is the resultant for reactance. Now current means epsilon RMS by XL now. So by substituting this value, finally we are getting here 15.9 amps. That is what RMS value of current what he is asking. Okay, right. In our next problem, in our next class we will continue with exercise 4th problem. Thank you.